If you need to step 24 volts down to 5 volts, a standard linear regulator will easily do the job, but it burns off the remaining 19 volts as pure heat. To handle that, you have to attach a massive heatsink. A modern switching mode power supply IC makes the exact same voltage drop while staying entirely cool to the touch. To keep that linear regulator from melting under 19 watts of waste, you would need a heatsink larger than the actual device it's powering. That volume requirement is what forces us away from linear regulation and towards switching. Let's track how energy moves through one of these systems. Raw AC mains comes into a rectifier, gets stored in a bulk capacitor, is chopped up by a PWM MOSFET, stepped down through a transformer, and finally smoothed out by an output filter, all continually adjusted by a feedback loop. At each stage, the electrical energy physically changes state. It enters as an AC sine wave, turns into pulsating DC pulses after the rectifier, becomes a high-frequency square wave at the switch, and exits as a flat, smooth DC output. Understanding this precise sequence of state changes is the baseline requirement for designing high-efficiency hardware. We start at the wall. Standard 230-volt AC mains is highly volatile. That 230 number is just an RMS average. The actual instantaneous peaks hit 325 volts, packed with unpredictable line transients that can destroy unprotected circuits. When you first apply power, the large bulk capacitor is completely empty. Electrically, it acts like a dead short. It immediately pulls a massive inrush current, sometimes exceeding 150 amps, which can blow your rectifier diodes apart. To prevent this, we add a front-end protection stage. Fuses catch hard faults, metal oxide varistors clamp high-voltage transients, and an NTC thermistor provides high initial resistance to choke that 150 amp inrush down to a safe level. Next, we size the bulk capacitor. The math for this relies on the ripple voltage equation. If we are on a 50 Hz main system and we want to allow 5 volts of ripple for a 2 amp load, take a second and try to calculate the required capacitance. You need 4,000 microfarads to keep that voltage stable. Managing raw mains input requires engineering robust physical safeguards against unpredictable power surges. Once the front end is stable, we reach the actual switching stage. In a standard buck converter topology, a MOSFET rapidly switches on and off. By adjusting the duty cycle, the ratio of on time to off time, we chop the high DC voltage into a precise step-down value, using an inductor to store energy and a capacitor to smooth it. Running high currents at high frequencies introduces a physical problem. You can no longer treat your PCB traces as perfect wires. At these speeds, every millimeter of copper acts as a parasitic inductor. This is a layout of a switching schematic. Notice the thin, meandering traces and widely spaced components. These long trace loops essentially act like antennas, radiating electromagnetic interference that will cause the entire system to fail. Now look at this layout. The components are tightly clustered, and the power traces are as short, direct, and thick as possible. We also arrange the components so the switching current loops curl in the exact same direction, which prevents magnetic field reversals. In SMPS design, your physical PCB layout is a critical, active component of the circuit that dictates whether the converter functions or fails. When you need to bridge the isolation barrier between mains and your output, the Flyback Converter is a standard solution for power levels under 150 watts. Instead of a traditional transformer, a flyback uses a coupled inductor to store and then release energy. The operation relies on strict timing, known as the dot convention. During the on phase, the primary switch closes. A magnetic field builds up in the primary core. Crucially, the secondary diode is reverse biased, completely blocking any energy from transferring to the load. Then comes the off phase. The primary switch opens. The magnetic field suddenly collapses, causing the voltage to fly up. This forward biases the secondary diode, and the stored energy finally dumps into the output. Mastering this sequence of energy storage and delayed transfer provides the necessary isolation to bridge high-voltage mains to low-voltage DC safely. Even with perfect theory, real-world parasitic capacitance and inductance still exist. This raw oscilloscope capture shows what happens at the switch node, a massive 65 MHz ringing overshoot caused by the inherent LRC resonance of your physical components. Look at the waveform now. By placing an RC snubber network across the switch, we actively damp that resonance. The simple resistor-capacitor combination absorbs the chaotic ringing, leaving a clean, manageable signal. Beyond signal integrity, there is the matter of physical safety. Even after the device is unplugged from the wall, that 400-volt bulk capacitor can hold a lethal charge for minutes. You must engineer a bleeder resistor directly across that bulk capacitor. It automatically drains those lethal voltages the moment mains power is interrupted, protecting anyone working on the board. Successful hardware design brings these pieces together: the energy path, the ripple math, tight loop layout rules, and mandatory safety components like bleeder resistors. Linear regulators are simple, but they burn power we can't afford to lose. Apply these high-frequency switching principles, respect your layout's physics, and design your next power supply.